We have now found more than 6,000 worlds orbiting other stars. 6,000. And every few months, a headline announces another one. Earth's twin discovered. Second Earth found. Potentially habitable super-Earth spotted. Just recently, astronomers published a fresh shortlist. Out of all 6,000 plus known exoplanets, they narrowed it down to the 45 most likely to be able to support life. 45 candidate second homes hanging out there in the dark. So here's the question everyone really wants answered. Is one of them our backup? If Earth ever became uninhabitable, is there a planet out there we could actually move to? Which world could replace the one we have? Today we're going to look at the real top candidates, the actual planets scientists are watching most closely, including the newest data from the most powerful telescope ever built. We'll see what makes each one tantalizing, and then we'll confront the brutal, sobering catches that the headlines almost never mention. Because the honest answer to which planet could replace Earth turns out to be one of the most humbling things in all of science. Let's get into it. First, we need to define what we're even looking for, because another Earth has a specific scientific meaning. The magic concept is the habitable zone. Astronomers sometimes call it the Goldilocks zone. It's the band of distance around a star that's not too hot and not too cold, but just right. The region where a rocky planet could have liquid water on its surface. Too close to the star and your water boils away. Too far and it freezes solid. Liquid water is the one non-negotiable ingredient we know life needs. So the habitable zone is where the search begins. But, and hold on to this because it becomes the whole point later, being in the habitable zone is just the bare minimum. It means a planet could have liquid water. It absolutely does not mean it does, or that anything else about the place is survivable. A planet in the Goldilocks zone can still be a lifeless, airless, radiation-blasted rock. Right distance from the star is the start of the conversation, not the end of it. We don't even have to leave our own solar system to see how treacherous in the habitable zone can be. Venus sits at the inner edge of our sun's habitable zone. By distance alone, it's a perfectly reasonable candidate for life. It's nearly Earth's twin in size and mass. And it is one of the most hellish places imaginable. A runaway greenhouse atmosphere of crushing carbon dioxide, surface temperatures hot enough to melt lead, and clouds of sulfuric acid. A planet that should have been Earth's sister became a furnace, mostly because of what happened to its atmosphere. Now consider that astronomers have already found exoplanets nicknamed exovenuses, worlds in the habitable zone that, like Venus, may be searing greenhouse traps rather than gentle blue oceans. This is the cautionary tale baked into our own backyard. The same starting distance can produce a paradise or an inferno, and from light years away, we often can't tell which is which. The habitable zone tells you where to look. It tells you almost nothing about what you'll find. With that in mind, scientists have built catalogs ranking the best worlds. One recent effort identified around 70 potentially habitable planets, of which roughly 29 are likely rocky with the possibility of liquid surface water. They even score these worlds with something called the Earth Similarity Index, a number from 0 to 1, where 1 would be a perfect Earth twin. And this list keeps getting refined with fresh data. In early 2026, a team at Cornell published what some compared to a real-life version of the rescue mission in the film Project Hail Mary. Out of the more than 6,000 exoplanets known at the time, they pinpointed the 45 rocky worlds most likely to be potentially habitable. A focused target list to aim our best telescopes at, and the discoveries keep coming. In late 2025, astronomers announced a promising new super-Earth in the habitable zone of a small red dwarf just 18 light-years away, detected by the gentle gravitational tug it exerts on its star. Instantly one of the nearest interesting targets we know of. The count of confirmed exoplanets, around 6,000 at the start of 2026, climbs almost every week. We are living through the most productive era of planet hunting in history. And yet, as we're about to see, more planets has not meant finding a home. It's meant discovering, over and over, just how hostile most of them are. So who's at the top of the list? Let's meet the contenders, starting with the one right next door. But first, a quick word on how we even know these worlds exist. because it explains why our knowledge of them is so frustratingly thin. We almost never see an exoplanet directly. They're tiny, dark, and drowned out by the blinding glare of their star. Instead, we detect them by their effects. The main trick is the transit method. When a planet passes directly in front of its star from our point of view, it blocks a tiny sliver of light, and the star dims by a fraction of a percent. Measure that repeated little dip, and you can work out the planet's size and orbit. The second trick is the radial velocity method. A planet's gravity tugs on its star, making the star wobble ever so slightly toward and away from us, which we can read in its light. That wobble reveals the planet's mass. Put size and mass together, and you can estimate density, whether a world is likely rocky like Earth or puffy and gaseous. But notice what that gives us. Size, mass, orbit. That's almost all we get for the vast majority of these planets. Whether they have air, water, clouds, a magnetic field, a breathable sky, all the things that actually decide if you could live there usually remain a complete mystery. This is why we found an Earth-sized planet in the habitable zone is so much less than it sounds. We've measured the easy things and learned almost nothing about the things that matter. There is one powerful exception, and it's changing everything. When a planet transits its star, a little starlight filters through the planet's atmosphere on the way to us, and different gases absorb different colors of that light. By splitting that light into a spectrum, the most advanced telescopes can read the chemical fingerprints of what's in the air: water vapor, carbon dioxide, methane. This is the technique now letting us, for the first time, actually interrogate these distant atmospheres instead of just guessing. But it only works well for a lucky few nearby planets. And even then, it's at the absolute edge of what's possible. Keep that in mind as we meet the candidates, because it's the difference between a planet we can dream about and one we can actually test. Our first candidate is the closest possibly habitable planet to Earth that exists, Proxima Centauri b. It orbits Proxima Centauri, the very nearest star to our Sun, just over 4 light-years away. When it was announced in 2016, it was electrifying, an Earth-sized planet in the habitable zone around the closest star to us. It was almost too perfect. The planet is at least about the mass of Earth, sits at the right distance for liquid water, and gets a decent amount of warming energy from its star. On paper, it's the dream, a near-Earth mass world in the Goldilocks zone, practically in our backyard by cosmic standards. If you wanted a backup Earth, this is the first place you'd look. And then reality shows up. Proxima Centauri is not a star like our Sun. It's a red dwarf, small, cool, dim, radiating a tiny fraction of the light our Sun puts out. And that creates 2 enormous problems that, together, may doom the whole idea. The first is that to be warm enough for liquid water around such a faint star, the planet has to huddle extremely close. Proxima b orbits more than 20 times closer to its star than Earth orbits the Sun, whipping around in just over 11 days. And the second problem is the killer. Red dwarfs are violent. Proxima Centauri is what's called a flare star. It erupts with sudden, brutal outbursts of radiation. Its brightness can spike by a factor of 100 over a matter of hours. And because the planet is hugging the star so tightly, it gets blasted. Studies modeling an Earth-like atmosphere on Proxima b found that the star's radiation could strip that atmosphere away as much as 10,000 times faster than the Sun erodes Earth's. One observed superflare was so powerful that scientists concluded it could, over time, have evaporated the planet's oceans and sterilized its surface entirely. So our closest, most exciting candidate may well be an airless, irradiated rock, close enough to taste, but possibly already dead. And here's the thing, Proxima b's problem isn't unique. It's the problem with almost every nearby candidate because of one uncomfortable fact about our galaxy. The most common stars by far, about 3 out of every 4 stars in the sky, are these small, cool red dwarfs. So when we hunt for nearby habitable planets, we keep finding them around red dwarfs, and they keep running into the same 2 brutal obstacles. The first is tidal locking. When a planet orbits that close to its star, the star's gravity grips it and slows its spin until one side permanently faces the star, and the other faces away, forever. the way the moon always shows Earth the same face. So instead of day and night, you get a world split in two. One hemisphere in eternal, scorching daylight, the other in eternal, frozen darkness. The sun-facing side bakes. The far side is locked in permanent deep freeze. Maybe, just maybe, there's a thin ring of livable territory in the twilight zone between the two extremes. But it's a far cry from the gentle day-night rhythm that life on Earth depends on. The second obstacle is those flares we just saw. The relentless radiation that red dwarfs spit at their tightly orbiting planets, threatening to tear away any atmosphere before life could ever get comfortable. This is the central frustration of the search. The most common and most easily found planets sit around exactly the kind of stars that may be least friendly to life. Which brings us to the most famous planetary system of all, the one that made headlines around the world, TRAPPIST-1. About 40 light-years away sits another red dwarf, and around it orbit not one, but 7 Earth-sized rocky planets, several of them in or near the habitable zone. 7 worlds in one system, tightly packed. If you stood on one, the others would loom in the sky like moons. It's the richest collection of potentially Earth-like planets we've ever found around a single star, and several of them, usually labeled by letters, planets E, F, and G, sit at distances where liquid water could, in principle, exist. TRAPPIST-1e, in particular, has long been considered one of the very best candidates for a habitable world anywhere. It's almost exactly Earth's size, just a touch smaller, and well placed in the zone. The system itself is almost surreally compact. All 7 planets orbit closer to their star than Mercury orbits our sun, completing their years in a matter of days. They're packed so tightly and their orbits are so finely synchronized in a gravitational lockstep that the whole system behaves like a piece of cosmic clockwork. Each planet's pull nudging its neighbors in a delicate, resonant chain. Because the star is so small and dim and the planets so close, an observer standing on one of these worlds could look up and see the neighboring planets hanging in the sky as disks. Some larger than our moon appears to us. It's a genuinely beautiful picture. A cluster of worlds huddled around a tiny ember of a star. And it made TRAPPIST-1 the crown jewel of the search, the system everyone pinned their hopes on. But TRAPPIST-1 is also where the newest, most powerful telescope in history has started delivering some sobering reality checks. The James Webb Space Telescope has been studying this system intensely, because by watching starlight filter through a planet's atmosphere as it crosses its star, Webb can actually start to sniff out what that atmosphere is made of, or whether there's an atmosphere at all. And the early results have been humbling. For several of the inner TRAPPIST planets, Webb found little to no sign of any substantial atmosphere. They may be bare rocks, their air long since stripped away by the star, and recent observations of TRAPPIST-1e, the Great Hope, suggest it may have lost its original atmosphere too, though the data is still limited and the jury is genuinely still out. The point is profound. For the first time, we're not just guessing about these worlds based on their distance from the star, we're actually measuring them. And the measurements are reminding us that Earth-sized and in the habitable zone can still mean airless and dead. Now, our third candidate takes us somewhere stranger and, for a brief moment recently, more thrilling than anywhere else. A world called K2-18b, about 120 light-years away. This one isn't a rocky Earth twin at all. It's bigger, somewhere between Earth and Neptune in size. And scientists think it might be a Hycean world, a planet covered by a global ocean of liquid water beneath a thick hydrogen atmosphere. It orbits its red dwarf every 33 days, and it has a real pedigree as a target. Back in 2019, astronomers detected water vapor in its atmosphere, a first for a habitable zone planet, and later found carbon dioxide and methane there too. That combination is exactly why it became such a focus. And in 2023 and again in 2025, observations with the Webb telescope set the world on fire because researchers reported a possible detection of a molecule called dimethyl sulfide in its atmosphere. Why does that matter? Because on Earth, that molecule is produced almost entirely by life, most by ocean plankton, a possible fingerprint of biology on a distant world. For a few days, it felt like we might have found the first hint of alien life. But this is exactly where science earns its reputation for caution. And it's worth slowing down. Almost immediately, other scientists pushed back hard. When independent teams reanalyzed the very same telescope data, several found that the evidence for that life-related molecule was statistically weak, not nearly strong enough to claim a detection. Worse, they showed that other, completely non-living chemicals could produce nearly the same signal in the data, and that the apparent detection was sensitive to exactly how you process the numbers. The honest current status is, it's a fascinating hint, not a discovery, and most of the field thinks the claim is, at best, unproven. K2-18b remains a tantalizing target, a world that might have an ocean, might have life, or might just have unusual chemistry and bad gas. It's a perfect lesson in how the search for a second Earth really works. Extraordinary claims need extraordinary evidence, and we're not there yet. There are other names on the list too. LHS-1140b, a super-Earth around 50 light-years away that's become a top target because it might actually hold on to an atmosphere. Recent studies have even raised the tantalizing possibility that it could be a water world or hold a liquid ocean. And crucially, it orbits a calmer, less violent red dwarf than Proxima, making it one of the rare nearby candidates that hasn't been immediately ruled out by its star's ferocity. Teegarden's star B, just 12.5 light-years away, one of the most Earth-similar worlds by the numbers. Distant Kepler discoveries with names like Kepler 442b, rocky and well-placed, but hundreds or thousands of light-years away. So faint we may never learn much about them. Each one is a flicker of hope. And each one, when you look closely, comes wrapped in the same fog of uncertainty. We know its size, roughly its orbit, and almost nothing else that actually matters for whether a human could survive there. It's worth being honest about why the Kepler planets in particular stay so mysterious. The Kepler Space Telescope was a phenomenal planet-counting machine. It found thousands of worlds by watching for those tiny transit dips, but it stared mostly at distant stars, hundreds or thousands of light-years off. That's wonderful for statistics. Kepler taught us that planets are everywhere, that rocky worlds in habitable zones are common across the galaxy. But it's terrible for getting to know any individual planet, because those stars are far too faint and far for us to study their planets' atmospheres in any detail. So we have this strange situation where we're confident the galaxy is full of potentially habitable worlds, by some estimates billions of them, while knowing almost nothing concrete about nearly all of them. And the next great planet hunting tool, a space telescope launching in 2027, will use yet another technique. Watching for the way a planet's gravity briefly bends and magnifies the light of a background star, that's expected to find thousands more worlds, including many in habitable zones, but often so distant we'll never visit or even closely examine them. We are building an ever larger census of places we cannot reach. And that points to the single most important truth in this entire subject, the catch that quietly dismantles the whole fantasy of a backup Earth: its distance. We have to talk about distance because the numbers are almost incomprehensible. Proxima b, remember, is the closest one, the closest possibly habitable planet that exists. It's 4.2 light-years away. That sounds almost cozy. But a light-year is about 6 trillion miles, which means Proxima b is roughly 25 trillion miles from Earth. To put that in human terms, the fastest spacecraft humanity has ever launched would take tens of thousands of years to cross that gap, longer than human civilization has existed. Our most distant probe, Voyager 1, after nearly 50 years of flying, hasn't even covered a fraction of 1% of the way to the nearest star. With any technology we actually possess, a journey to even the closest candidate is not a trip. It's a multi-thousand-year, multi-generational impossibility. And that's the nearest one. TRAPPIST-1 is 10 times farther. K2-18b is 30 times farther than that. Kepler 442b is so far away, its light takes over 1,000 years to reach us. These are not places we can move to. They are places we can barely even photograph. So let's put the brutal reality together, because it reframes the entire question. To replace Earth, A planet would need to clear an almost impossibly long list of hurdles, all at once. It needs to be the right size, rocky, not a gas ball. It needs to be in the habitable zone, the right distance for liquid water. It needs to actually have water. It needs a stable atmosphere, thick enough to breathe and to shield the surface. It needs protection from its star's radiation, ideally a magnetic field like Earth's. It needs to not be tidally locked into a half-frozen, half-baked hellscape. It needs gravity close enough to Earth's that our bodies could function. And after clearing every single one of those, it needs to be close enough that we could conceivably get there, which, as we just saw, none of them are. When you stack all those requirements together, the staggering truth emerges. Among the 6,000 worlds we've found, we do not currently know of a single one that we could confirm checks all those boxes. Not one verified, ready-made second Earth. We have candidates, we have maybes, we have planets that are the right size and the right distance, but a true replacement for Earth, a place a human could step out and breathe, has not been found and may be vanishingly rare. And it's worth lingering on just two of those hurdles, because they're the ones the fantasy always skips. The first is gravity. We talk about Earth-sized planets, but many of the most common worlds out there are super-Earths. Rocky planets several times more massive than ours. Stand on a heavy super-Earth, and you might weigh half again as much as you do now, or more. Every step a struggle, your heart laboring against a pull your body never evolved for. Go the other way, to a low-gravity world, and we already know from astronauts that prolonged weak gravity wastes muscle and leaches calcium from bone. A planet has to thread a surprisingly narrow gravitational needle for a human body to actually thrive on it long-term. The second hurdle is the one we just keep slamming into: an atmosphere and a magnetic shield. Earth isn't just lucky to have air. It has a molten iron core generating a magnetic field that deflects the worst of the sun's radiation and helps keep our atmosphere from being blown away. Take away that invisible shield, and even a perfectly placed planet slowly loses its air to space and bathes its surface in radiation. We almost never know whether a given exoplanet has one. It's the difference between a living world and a sterile one, and it's nearly invisible to us. So if finding a ready-made Earth is this hard, you might ask the obvious next question: could we make one? Could we take a hostile but promising world, a Mars-like or Proxima-like planet, and terraform it, deliberately engineering its atmosphere and temperature until it's livable? In principle, it's a real idea scientists discuss: thickening a thin atmosphere, warming a frozen world, seeding it with the right gases over centuries. But in practice, terraforming an entire planet is a project of almost unimaginable scale and time, likely thousands of years, with technology far beyond what we have, and no guarantee it would hold without a magnetic field to protect it. Terraforming turns find a second Earth into build a second Earth, which is arguably even harder. It's a fascinating long-term dream, but it is not a backup plan for any crisis we can foresee. And honestly, that should change how we think about this whole search. Because here's the twist: the scientists pointing their telescopes at these worlds mostly aren't looking for a place to evacuate to. They know we can't get there. What they're really hunting for is an answer to a far deeper question. Not where can we move, but are we alone? The new generation of instruments being built right now, a powerful new space telescope launching in 2027, giant ground-based observatories coming online at the end of this decade, and a dedicated planet-studying observatory planned for the 2040s are designed to do something breathtaking: to analyze the atmospheres of these distant worlds and look for the chemical fingerprints of life, not to find our next home, but to find out if we have neighbors. So what's the real answer to which planet could replace Earth? The most honest one is humbling, and maybe even beautiful. As far as we can tell, with everything we currently know, no planet can replace Earth. Not Proxima b, not TRAPPIST-1e, not any of the 45 candidates on the shortlist. Every one of them is either probably hostile, completely unverified, or so far away it might as well be in a dream. The perfect, gentle, life-soaked, breathable world. the one with the right air and the right gravity, and the right light and liquid water under an open sky. We've only ever found one of those, and we're standing on it. The search for a second Earth has, more than anything, revealed how staggeringly rare the first one might be. 6,000 worlds and counting, a galaxy full of rock and fire and frozen dark, and one pale blue dot where, against all the odds, you can walk outside, take a breath, and live. We keep looking up, hoping to find another, but so far, the best planet ever discovered for human life is the one already under your feet, and we'd be wise to treat it that way.